All right, so some more of the same on the next page. So I'm gonna put a big old star here. So take a look at these for homework. Too crazy. This stuff, it doesn't ever really get too bad, at least not in this course. Integration is a course in and of itself in college, so you'll spend plenty of time working with this material down the line. But for now, it's really just the basic stuff. And to think that what we covered, in the last unit or so is the quote-unquote basic stuff is kind of alarming, but that is in fact what it is. Anyway, so this is still under that category. 0 to 6, the interval for this integral of function f of x dx. So they gave us our little given statements here, and just like we did yesterday, we need to kind of piece together that information to get appropriate solutions. Some of them are easier than others. You might look at problem C right off the bat and know that answer, right? But A, you got to do a little bit of background work before you can get started, right? And that's to say that, well, I don't know it from 0 to 6, but I do know 0 to 3, and I know 3 to 6. If I add those together, then I'll get what I'm looking for. I'll get the interval going from 0 to 6. Right? So this is some rule for definite integrals. Right? If you were to diagram this out, and you don't really need to, but in order to understand it fully, you might want to. You have 0 to 6, some function f of x, partitioned to 3. They're telling us that the first piece is 4, and the second piece is -1, which it doesn't really coincide with my diagram because the second piece should be below the axis, but just the idea of piecing two areas together to get the whole is really what we're after here. So in this case, we're looking at 4 plus -1, which would give me a 3. All right, for part B, looks like the bounds are the exact opposite of one of the givens. All right, one of our properties tells us that we can swap the bounds as long as we negate the integral. All right, so we're looking at -1, which would be equal to 1. Part C, like I said, that's the easy one because you're not going anywhere, so you wouldn't accumulate or lose any area. And the last one is the constant multiple rule for definite integrals. So pull out the -5 on the interval of 3 to 6, f of x dx. 3 to 6 was given as -1, so we're taking -5 and multiplying it by -1. All right, so not too bad. All right, but this is a little bit of a twist on what we were talking about because here we're not given the function itself, so there's no way around it. You have to use the given information. Right? Whereas in the case of the trig functions, we did sine, cosine functions. We did some polynomial functions. Those you could pop into the calculator, if it's a worst case scenario type of deal. But these, the calculator's not going to help you because you don't know what the function is. All right, same idea with the next example. This one might even be a little juicier because it requires you to really fully understand what a definite integral is telling you. Right? What it's actually giving us is the net area over an interval. All right, so net area over an interval. All right, and what that means is that there's a lot of increases, decreases potentially on an interval. This is the resulting area at the end of that particular interval. So I always equate it to snowfall. So if you're looking at, like a wintry season, you have some snowy days and some days where it's warmer. So on the snowy days, you accumulate snow. On the warmer days, you lose some snow. The snow melts. Right? So the heights of the snow on the ground is variable over time. Right? What this would tell us is what the height of the snow is on day 6 or after the 6th day. Right? So there was some snowfall, there was some melting, there's maybe some more snowfall, some more melting. This is the resulting height of the snow after that last moment, the last moment that you care about. Right? If you go too far though, the snowfall analogy falls flat because it would go to 0 eventually. And it wouldn't allow for any negative quantities. Right? You wouldn't ever end up with negative, let's say, 10, because that would mean we'd have to have negative snow. I don't know what that would look like.
Snow falling back to the sky.
Yeah, the other way, right? Like a dusting. Infinity War. Endgame, damn it. Thursday night, but mine's Friday evening, 7:30. Saturday. Alamo Draft House, dine-in movie theater. I will be getting the baked pretzel with the queso dip and the spicy mustard. Potentially the Greek salad with chicken. Possibly the kids' pizza. The adult portion is too much. It's way too much.
Are you allowed to order that?
Yeah, I just bring a kid with me.
Oh, there you go.
Yeah. Just find one in the parking lot. Yeah, bring him in. Order a kid's pizza and send him on his way. What's the other thing? Oh, the fried pickles. Can't go wrong with them. Fried pickles are legit. I'm not a big fan of the dipping sauce, the ranch dipping sauce. It's not for me. Pickles bring their own flavor, so you don't need to dip it in anything. What else do we do? The Alamo Draft House in Yonkers on Central Ave. It's legit. All right, so this is telling us that the region A has an area of 1.5, but that doesn't really coincide with the diagram, because according to the picture, that area should be negative because it's below the axis. Right? So what they're giving us is an absolute area. Right? So they're giving us the absolute value of the area over an interval. All right? So absolute value all right. They define that as the total area. They being the calculus textbook writers, AP exam writers. All right, so basically if you're just disregarding the negative sign, then you're talking about a total area. Right? If you're including a possibility of an area being negative, then that would fall into the category of being a net area. Right? But anyway, so what that's telling us is that the definite integral from 0 to 2 of my function f of x dx would be equal to negative 1.5. Right? Because definite integrals do allow for negative results. All right? They're also telling us, flat out in the problem, that on the interval of 0 to 6, we have 3.5. All All right, so with those two pieces of information, we could pretty much answer everything that was asked, because the first question is directly asking us what the definite integral was on the interval of 0 to 2, which we just stated was negative 1.5. The second problem is the sum. So we could break up the sum. Using the sum rule. All right, what is the definite integral on the interval of 0 to 6 of 2?
12.
12. Very good. 12, and then the other one was given to us as 3.5, so we know that this is going to be 15.5. All right, the next one is asking us for the antiderivative, or the definite integral over the interval of 0 to 6 of the absolute value of the function with respect to x. Now, this goes way back to something that we talked about September-ish. I mean, it really doesn't matter. It was a long time ago. That's the whole point. If you need to create on the fly, without a calculator, the graph of an absolute value function, all you have to do is reflect the negative parts over the x-axis. All right, so that's telling us that we would take this guy and make it look like meh. So this curve and its corresponding area, I'll shade it all in, would be the absolute value of the function f of x. Get a little more in there. All right, so all we'd have to do is figure out what each of those pieces are. Well, we kind of sort of know. I mean, we definitely know A. I'll bring that back in for a sec. We know that that's 1.5. All right. The only reason we made it negative to begin with was because it was below the axis. All right. Now, we also know that the net area over the interval was 3.5. All right. So if I went with the original graph, right, if I took this guy here, which was negative 1.5, and then region B, and added those together, the result should have been equal to 3.5. If that's the case, then region B has to itself be equal to 5. I just add the 1.5 to both sides. All right, so that gives me that piece. So on the interval of 0 to 6, all I would need are the sum of those two pieces, 1.5 and 5, and I'd have it. All right, but it comes down to the idea of recognizing what an absolute value of a function looks like. All right, and again, I mean, you have the calculators in front of you right now, but you may not when it comes time to take a test or the AP. So, you know, it's something that you need to be able to reason in your mind, not necessarily on paper, even just like upstairs. For D, that's probably the easiest one now because it's constant multiple. If we just skip all the writing step and just jump right to the final answer, we're looking at -2 multiplied by our answer to part A, and it's going to give us a 3. I'm going to, the remaining time that we have, tackle these trig problems with you. They give you a nice rule here, being given that from 0 to pi, the sine function contains an area of 2. And using what you know about integrals, graphing curves and using a little bit of intuition, maybe a lot, determine the values of the following integrals. All right, so just quickly draw a nice little sine function here. I'll do it over 0 to 2 pi, just to get the full wave. They're telling us from 0 to pi, which would be the halfway point, that contains an area of 2. All right, I'm going to split it up even further. Put a pi over 2 here, a 3 pi over 2 here, and I'll get the 2 pi here. All right. If I know that I have an area of 2 on this whole interval from 0 to pi, what do I know about this subinterval? What's its area going to be? Half of that, which would be 1. All right. So I know it's going to be 1 unit. Intuition. All right. The idea being that we know that there's symmetry in a sine function. All right. Now it looks like we have some point symmetry here through pi comma 0. What's this subinterval's value going to be? From pi to 3 pi over 2. Well, it's below the x-axis. -1. All right, so we have all that information, which means that if I needed to, for example, figure out, bless you, the area from 0 to 2 pi, bless you, it would be an area of 0, all right? Because I have equal parts positive area and negative area, so they cancel out, all right? If I needed to find 0 to 3 pi over 2, I can do a quick sum and get it. It would be just a positive 1. All right? But that sets me up for a lot of the problems that follow. All right? It asks me for pi to 2 pi. -2. 0 to 2 pi we already really addressed. Just by drawing the diagram. 0 to pi over 2 already accounted for. For D, it's a little different, but nothing too crazy. It's just what I want to do here is use one of my properties first, and that's the sum property, 0 to pi of 2 dx plus 0 to pi of sine x dx. All right, so what is the definite integral on the interval of 0 to pi of 2 dx? 2 pi. And then the other one? Just a 2. Either from the diagram or from the given, either way. All right, for E, we have a little constant multiple action going on there. So I could pull out the 2. So 2 multiplied by, same deal, right? 2 multiplied by 2. And we'll get a 4. Gets a little funkier after that. Part F doesn't seem anywhere related to the given function, but it's very related. I'm going to draw a quick sketch of that, and you'll see. It's kind of off on the side here. By the way, quick question. What does that x minus 2 tell us? Move it to the right. Yeah, it's a horizontal shift. Right? In this case, it's 2 units. Right? The coefficient of x is 1, so it's definitely a 2-unit shift to the right. Right? So instead of starting off at x equals 0, it's going to shift to 2. And then instead of having a max, I'll just draw the full original sine wave. I'll extend this. Instead of having a max at pi over 2, it's pi over 2 plus 2, and then pi plus 2 for the midline, and so on. So it's going to look something like this. All right, so what I get from this is that it's the same sine function, just shifted over. I'm looking for the area between 2 and this location, which would be pi plus 2. Sorry, 2, that's not pi plus 2. That's 2 pi plus 2. This one would be pi plus 2. So I need this area, which would be what? 2. Once you realize it's the same figure as what we started with, then you can work off of that. Although that's a much nicer drawing than the original one. The dotted black, I mean, that is just beautiful. I mean, that's a gorgeous diagram. Anyway. I don't even know how that happened. Now this one seems to be a change in variables, but it's actually the easiest problem on the whole page. It's just zero. All right, so just a quick sketch. I'll just do it like this. Oh boy, I had to make up for the good drawing. So what it's telling us is that we have, and now u, I mean, in this case, it could be replaced by x's. It really would make a difference because we're dealing with the bounds going from negative pi to pi, but these bounds are in terms of u, right? So it's really the same function. Maybe it has some composite aspect to it, but it's going from constant bounds, so it leads me to think that that's probably not the case. All right, so negative pi, positive pi, 2 areas that would offset each other. All right, so equal parts positive and negative. All right, but even if it were, some other inner function, you have that point symmetry through the origin. All right, because the sine function is an odd function, if the bounds are opposite of one another, they're always going to cancel out in terms of area. All right, so that always is going to happen with odd functions. If you had an even function, that's a different story. You would actually just double it. It would be, if you were going from negative pi to pi, but for, let's say, a cosine function, whatever the 2 parts are on either side of the y-axis, those would be equal to one another. All right. Now, for h, what do we have here? What does that x over 2 tell us? It's a constant multiple of x, but how does that impact the graph? It affects the period. Okay, so the period is 1/2. I'm sorry, the frequency is 1/2. The period 4 pi. All right, so it's double the width. All right, so what that's telling me, oop, that's a highlighter, is that I'm going to get the same height, because the amplitude is still 1, of the sine function, but it's going to be double the width. Right? So where I would have to go out to 2 pi normally to create one full sine wave, I'd have to go out to 2 pi to only get half of a sine wave, all right? Or 4 pi to get the full thing. But if I look at it this way, poor quality. Not much better. All right, so I've doubled a single dimension. So what's going to happen to my area? Double. All right, so instead of 1 and 1, it's going to be 2 and 2. All right, so this would be 4. Last one's cosine wave from 0 to pi. Let me do the full shebang, poor quality. But as you know, a cosine wave is just a shifted sine wave. All right, so if I break this up into parts like I did for the sine wave, each of these areas would have the same quantity. So from 0 to pi, I'd have a total of what? 0. All right, so I'm going to put a star on examples 5 and 6. So the problems that I start on the previous page and also these, do those for homework, and we'll go over those tomorrow. The function, or the integral. All right, so what that is telling us is to not actually integrate this by hand, because you might remember this from the last unit or 2 units ago as not being an easy problem. All right. The square root of a constant minus an x squared, that has a look of an arc sine, which would mean a trig identity substitute, not a trig identity, just a trig substitution. All right, which, you know, draw the triangle, the u, the a's, substitute in, it would be fun. So let's not do that. Instead, let's take a look at just this guy, because we know that when we're finding a definite integral, we're finding an area, right? And the area is y times dx. Right? So y has to be equal to the square root of 4 minus x squared. All right, so let's clean this up a little bit. Square both sides. And get it into standard form. And you end up with something that's much more recognizable. Okay. Now, you may not have even known to look for this, but you know, if you do have the ability to use your calculator, you still don't want to do this by hand. You might consider just using Math 9 and just popping it right in. But you might also consider just taking a look at the picture and seeing that it's the top half of a circle. All right, so it's a semicircle. And so you know the area of this already. All right, so if I were to sketch this out, going from -2 to 2, I'm just talking about this. All right, and I know it's the top half because it's positive. All right, that radical is positive. If it were negative, it would be the bottom half. But it wouldn't be both, because then it wouldn't be a function. All right, so we're looking for area of a circle, semicircle, pi r squared over 2. Radius is 2. So we're looking at 2 pi. Now, number 6, a little bit of a different story here. Not quite as recognizable, at least in its current form. But if we rewrite the function, absolute value of x over x, the absolute value of x could be rewritten as plus or minus x. plus or minus x divided by x would be equal to plus or minus 1. All right, so it would just beg the question of, all right, well, which one is it, the plus or the minus? So let's draw a graph real quick. We know we're going from -1 to 2.
Why? Do we know that?
Oh, the bounds. So I'll start by plugging in a -1. We wouldn't obviously plug it into the simplified form because there's nothing to plug in. Plug it into the unsimplified form. If I plug in a negative number to the unsimplified form, well, no matter what I plug into the top, it's going to be positive. So that's irrelevant. So whatever I plug into the bottom will dictate what type of piece this piecewise function would be. All right. So if I plug in a negative, it's going to be a negative result. If I plug in a positive, it's going to be a positive result. If I plug in 0, well, then it's going to be indeterminate. All right. So there's nothing going on at 0. All right. So there's a big old jump there. So I know that I'm living at -1. I'm living at -1 until I get to 0, at which point I'll jump on up to +1 for the rest of the trip. All right, so this bounded region would have an area. Now, this area is actually going to approach a particular value. It's not ever going to necessarily get there. So that's one little bit of funny business, I suppose, because you're not actually going to get to the y-axis from either direction. So to say that we're going to actually capture the area just using this particular technique is not fully correct. But what we could say is that the area is approaching what we get as a result here. So we're going to look for this value. It says a y value of 1. Sorry, -1. This one has a y value of +1 over an interval of 2. So this has an area of 2, area that's approaching 2. And this one has an area that's approaching, I gotta clean this up, it looks terrible, hold on. I'm labeling so much that it just looks awful. It's just going to look awful. Well, okay, I'll just do it in a different color. The area is approaching -1. We have a dimension of 1 by -1. Right? So if we read it from left to right, I have 1 unit over -1 in the y direction, so 1 times -1 is -1. So if I'm looking for the net area, I would just take the sum of those values. All right, so result is 1. All right, but again, it's really approaching 1. But in reality, whenever you're using the definite integral approach for finding areas, because it's a limit-based approach for finding areas, your answer is always that the area is approaching that particular number. Right? It's only when you use the geometry formula that you can say it's definitely that value. Right? So it's weird, but that's the way it works. And then later on in future math courses, you'll find that there's even more to this. It's crazy. Something called the double integral that'll blow your minds. All right, so what was it, April 23rd?
I know, I was thinking about that yesterday.
It's crazy. Only a couple weeks left in the course. So it seems like an appropriate time to talk about the fundamental theorem of calculus. That's the same thing with algebra. It's crazy. It wasn't until I don't even remember learning the concept, but it wasn't until I was teaching pre-calc that I came across a concept called the fundamental theorem of algebra. So, thank you. So you had to complete all of algebra before you tackled a concept called the fundamental theorem of algebra. So we pretty much covered all of calculus before we covered the concept called the fundamental theorem of calculus. It is what it is. But we've been kind of working off of this idea a little bit. The idea here is that if you have a definite integral, now there's two parts to the fundamental theorem. One part is the easy part. The other part is a little crispier, but that's a different story for a different day. All you're doing is you're taking the antiderivative and substituting your bounds in, and then subtracting the results. Right? So antiderivative of 3 with respect to t is 3t over the interval of 2 to 7. So all I'm doing is I'm taking 3, multiplying it by 7, and 3 and multiplying it by 2. So I'm substituting the 7 and the 2. So top bound minus the bottom bound.
No.
So you get a result of 15. All right, something the calculator does for you very easily. If you use Math 9, so Math 9, you just pop in the 2,
No, not certain.
the 7, the 3, and you can put in whatever variable you want. It understands, as long as there's consistency. If the function has x's in it, as long as you put an x in your d, then it's perfectly fine. I'm just going to use x here, so you get the 15 that way. So that's one way to do it. Obviously, dependent on your ability to use a calculator, whether it's allowed or not. So what this means is that there really is no difference in difficulty between a question like A, which was very simple, and a question like E, which would require you to do an identity substitution, perhaps. Well, actually, in that case, it's not bad because it's if you have the negative cosecant squared. Antiderivative of negative cosecant squared is what? Ten more quizzes. Antiderivative of negative cosecant squared? Just cotangent, yeah. So
It's negative cosecant.
because it's already negative.
Did you say square?
I did say
Oh,
square.
okay,
Yeah.
that's fine. 10 more bits.
Indeed. Yes, we will go with that. Plus cotangent x.
Okay, we're doing our best.
Did you have to
But I guess your best wasn't good enough. I wrote colors. So, yeah, a little bit of work. Cotangent of pi over 2 is what?
Oh no. Wait, cosine is sine. There's cosine. Cosine is
cosine of 90 is 0. Alright, so this one's going to zero out. And what is the cotangent of pi over 4? What's the tangent of pi over 4? Tangent 45 degrees? 1. Reciprocal of 1 is 1. All right, so that's going to be roughly about 0.57. So let's see what the calculator comes up with. Was it 2 minus cosine? So, yeah, the one issue is typing in the cosecant squared.
Oh, I see.
So we get something that is equivalent to the correct answer. So let's see if we can manipulate this to actually give us the exact form. So we know it has to be some multiple of pi, I suppose. So try dividing out the pi and see if that does anything. Okay. Because there's a sum or difference involved, it doesn't play out the way you want it to. So it's dangerous. If it were just like, for example, pi over 2 or 20 pi or something like that without the minus 1, the little trick of dividing out the pi would have worked. But because there's a minus sign in there, or subtraction, addition, any kind of operation like that, it messes things up a little bit.
When I do math 9, why does it look like yours? It's just like
You had it in classic mode, so it should be no problem. All right, so there's pitfalls that you have to worry about a little bit. Some of them are not bad. These are not crazy at all, but there are some cases where, depending on what kind of answer you need to come up with, you might need to resort to doing some stuff by hand. But if you're just looking for equivalence, then the calculator can get the job done for you. All right, so. All right, so the mean value theorem for integrals, because there was a mean value theorem for derivatives. I usually call this one the average value theorem just to distinguish it from the mean value theorem for derivatives. All right. If f is continuous on a to b, there exists some number c in the interval such that this rule is true. That rule comes from the definition of the average value theorem, which you can see below. It's this guy right here. So the average value over an interval is the net area divided by the length of the interval. All right. So that's where the 1 over b minus a comes from. Right? The interval goes from a to b, so that's the length of the interval. If you divide your net area by that length, you get the average value. What it's giving you is an estimator, a point estimate of the average height of the function, or average accumulated area, not height, of the function at any particular time along the interval. All right? So it's just a point estimate. It's not anything more than that. All right? But there you have the example 6 here, which is just kind of a play on that. So it's very procedural, though. All we have to do is just follow the model. So on the interval of 1 to 3, we have our function. I'll write it as 9x to the negative third dx. Should be equal to f of c. All right, so I'm going to write it as 9c to the negative third times the length of the interval, which would be 3 minus 1 is 2. All right, so I just have to find the antiderivative over the interval. So x to the negative second, so that's going to be negative 9/2. 18 c to the negative third. Gonna do a little subbing. All right, so plug in the 3. And then the 1. Clean it up. Now this amounts to 1/9, so that's going to cancel with the 9 there. So the first part of it's just going to be a negative 1/2. Then we're going to add to that, 2 negatives give a positive, 9/2. Whole thing will be equal to, I'll write it now as 18 over c cubed. So we're looking at 8/2, which is 4. And a little diagonal swappage. C cubed is equal to 18/4, which is 9/2. And so C would have to be equal to the cube root of that. So what that's telling us is that there is a value C, or it's not a proof, it's a demonstration, but there is a value C on this interval for which the average value is equivalent to the value itself at that particular time, moment. Right? So, and you can figure out the decimal value of that to make sure that it falls in the 1 to 3, but it's going to. All right. The problems after that is 7 and 8, much simpler, because it's just saying find the average value. So we're dividing the definite integral by the length of the interval. So we're looking at 1 over pi over 2 minus 0 times the integral from 0 to pi over 2 of the cosine function with respect to x. We'll crank that out in a sec, but I'll set up the last one also because it's pretty much the same idea. 1 over pi minus 0 from 0 to pi cosine x plus x dx. All right, so let's see what the calculator does for us here. Negatives. So that's clean. So the first one, so we take a shot, see if it gives us a clean answer. If it does, then we go with it. So this is just 2 over pi. And the last one, 0 to pi cosine x plus x. Not clean. Math bracket, not helpful. Divide by the pi. That looks familiar. That looks like pi over 2. So I divided by pi twice. So that amounts to pi squared over 2. Huh. Times 1 pith would be equal to pi over 2. All right.